So we will get started right now. So hi, this is our fourth meeting. This is our fourth class meeting, and today we will be talking about derivatives. So before I go on, does anyone have any questions about the homework on limits? Does anyone have any problems that they want to go over before we get started? No? Okay. So if you have any questions at any point, okay, the last question. Yes, so we will, I will actually go over that then right now. So for the last question, what? So for the last question, I will share my screen. Okay, so this was the last question. So we have this diagram here, and we want to show that, firstly, that 1 is bigger than or equal to sine of x over x. And then we also want to show that sine of x over x is bigger than or equal to cosine of x. And then we want to use those two facts to find the limit as x approaches 0 of sine of x over x. So which part of the problem do you want to go over? Feel free to speak out, like unmute yourself. Or is it like the whole problem in general? Okay, so I assume it's the whole problem in general. So okay. Oh, okay. Never mind then. I will go over it anyway because I think that this is actually a good question to go over. So the fact that 1 is bigger than or equal to sine of x. So here notice that if we have this diagram right here, we can think of this as a unit circle. So this red radius right here would be 1, and then this red color height right here would be sine of x. So this is right here is 1. This right here is sine of x, and then we also know that this right here, this line right here is 1, and so because of that, this right here is tangent of theta. And so this is actually kind of what you need to know. I'm not going to go over the details of these two proofs, so the proof of this fact and the proof of this fact. But once you have all the side lengths labeled, it is actually pretty easy from there. The important part is the actual part where limits come in. So notice that since 1 is bigger than or equal to sine of x over x on this interval in which 0 is contained, and sine of x over x is bigger than or equal to cosine of x on this interval where 0 is contained, we notice that when we take the limit as x approaches 0 of 1, we get 1. And when we take the limit as x approaches cosine of x, as x approaches 0 of cosine of x, we get 1 also. So we know that this limit right here is bounded between 1 and 1, and so it is also equal to 1. Yes. Hi, how are you? So that is essentially okay. So I just got a question in the chat. Couldn't you use L'Hopital? So you use L'Hopital when you already know derivatives. So right now I am assuming that, well, you don't know derivatives. If you do know derivatives right now, then yeah, that's the thing. So that is definitely a rule that we will cover in this course, and it's a very powerful technique for finding limits. But if you don't know derivatives, which is what we will cover today, you won't be able to apply it to a question like this. So it's really good that you already know about L'Hopital, but the solution that I had in mind was, without derivatives. But we will definitely get to that in this course. Okay. So in that case, then I will go to the presentation on derivatives. So this class will be about introduction to derivatives. We already kind of talked about derivatives in our first lesson, but today we will go a bit more in depth into what a derivative is, how it is defined formally with math, how we can write it down, and then some interesting relationships between continuity and a derivative. So one more problem that I want to go over from the homework, because some of the submissions I received for this problem, a lot of them were incorrect. Either they used this property to prove this property, or I don't know. There was one problem or another with the proofs of this property. So I just want to go over it now, just to clear up any misconception. So the question asked to prove that the limit as x approaches a of the log base any constant of any function, where the limit is defined, of course, is equal to the log base that same constant as the limit approaches of the limit as x approaches a of f of x. And so one of the properties that I already talked about in the previous class was the property right here, that the limit as x approaches a of a function raised to an exponent, so an exponent, a constant raised to a function, that is equal to that same constant raised to the limit of that function. And so what you can do here is plug in g of x equals log base c of f of x. And when we do that, we get this right here. So notice that here, c to the log base c of f of x, that is just f of x by definition of a logarithm. So this part right here just turns into the limit as x approaches a of f of x. And then we can take the log base c of both sides. The log base c of c to this power right here is just equal to the power. And so that is how it simplifies. So this is the proof. We use the exponent property here. And this is another very useful limit property that we will be using a lot. Okay. Now on to derivatives. So that's the one problem I want to go over before I moved on. Okay. So what are derivatives? Well, we already kind of talked about this in the first class, but a derivative of an output with respect to an input is an infinitely small change in output divided by an infinitely small change in input. So that is, and by the way, the infinitely small change in input has to be non-zero because otherwise we wouldn't be able to divide by it. But yeah, that is what a derivative is. So a ratio of infinitely small changes. And then derivatives measure instantaneous rates of change. So we can use algebra to find the average rate of change, but for the instantaneous rate of change, we need calculus to cover that, to actually calculate that. And derivatives have many applications, both in this course and outside of it. So in this course, we will, some of the stuff we will use derivatives for are optimization, so finding the maximum or a minimum way to do something, and evaluating limits. So as already noted, the limit of sine of x over x as x approaches 0, that we could have evaluated had we known what a derivative is, and it probably would have been much easier than what we had to do with the squeeze theorem without knowing. Yes. Yeah. So we will be talking about instantaneous velocity because that is an instantaneous rate of change of distance with respect to time. Okay. So yeah, instantaneous velocity, and that ties into physics, right? Because in physics, this is originally the context of calculus, that calculus came up in. So of course, I'm not going to be teaching you advanced physics, but definitely acceleration, velocity, position, stuff like that, and how they relate to derivatives, because those also go into the high school calculus curriculum. So basically, if you want to know physics or any other natural science, then you need to know calculus. Okay. So let's go back to the example of Newton and the apple. So the apple here is falling on Newton's head, and we have a graph of distance versus time. So notice that the apple is falling, and this is a graph of the distance versus time. So we can graph it like this. And then we went over in the first class how the instantaneous velocity is the instantaneous rate of change, the instantaneous velocity is the average rate of change between two infinitely close points. And by average rate of change, I mean the rise over run formula that we learned in, I don't know, pre-algebra. So if we have this black point, and if this black point is infinitely close to this red point, then the instantaneous rate of change at the red point is the same thing as the average rate of change between these 2 points. And between these 2 points, we can actually draw a line. And the instantaneous rate of change would be the slope of that blue line. And this blue line is called the tangent line because it only intersects this red curve at one point. It doesn't like cross over into the curve. And once again, you may say it intersects at 2 points, the red point and the black point. But since they are infinitely close, the difference between them is negligible, and we can say that it's just 1 point. So then to define how we would mathematically think about this instantaneous velocity, and by the way, this instantaneous velocity that we are calculating is a derivative of distance with respect to time. So the slope of this blue line, this tangent line, is a derivative. So this is what I'm talking about when I'm talking about derivative. So we can quantify derivatives by labeling the red point as x, comma f of x. So we can call this distance versus time relationship f of x. We can call it f of t. We can call it whatever we want. I'll call it f of x because that is how it normally appears in a calculus class. And then this red point is x plus h, comma f of x plus h. So the input is nudged by h, and the output is also nudged by some difference that depends on h. And notice that we want h to be really, really small, because then this black point approaches x, comma f of x. If h equals 0, then it is x, comma f of x. So let's write everything that we covered onto a new slide. And we have this kind of setup right here. And we want to find a mathematical formula for the instantaneous velocity, which is the slope of the tangent line. So this derivative of f of x with respect to x, that is once again the slope of the tangent line. This is the limit as h approaches 0 of the average rate of change. What this thing is telling us is as h gets closer and as this black point gets closer and closer to this red point, the average rate of change between these two gets closer and closer to the instantaneous rate of change at the black point. Then the average rate of change we can calculate using rise over run. So we can calculate this with change in y over change in x. Yes, so just I got a question about classes on YouTube. So these videos, I upload them to a Google form, and then Alphademic Learning will probably post them on YouTube in the near future. I do post the recordings on Google Classroom. If you are not able to view them because it says like we are not able to download this file at the time, then I guess you might need to wait a bit for the file to load. But they are on Google Classroom, and the recordings for the past 3 classes are also on Google Classroom. So if you need that at any time, you can always check that out. Yeah. Okay. Yeah. Glad I answered your question. Okay. So the change in y between these 2 points is f of x plus h minus f of x, and the change in x is x plus h minus x, which is just h. And so this right here is the formula that we will use for the derivative of f of x with respect to x. So this right here is a derivative. That is how we mathematically define a derivative. So for instance, if we're given a function like sine of x or something like that, or x squared, then we can try to evaluate this limit. We can plug x plus h into the function, subtract x from the function, and then we can subtract f of x from the function, divide that by h, and then calculate the limit, either using direct substitution or using some other method. So this is what a derivative essentially is. But always keep in mind that underneath the math and stuff like that lies the basic concept that is just a tiny change in output over a tiny change in input. So writing out this definition seems very messy. So mathematicians have developed a couple of shorthands for writing down a derivative. So one of these is this right here. So when you see, so this right here, I think is the most intuitive definition of a derivative. So as I went over in the previous class, in the first class, not the previous one, in the first one, this lowercase letter d in calculus typically means tiny change. It means not just tiny, but infinitely small change. So this makes sense, this definition right here, because it's a tiny infinitesimally small change in the function over a very small change in the input. And that is what a derivative is. That's the instantaneous rate of change definition right there. This definition is also, this notation is also very commonly used. You basically just bring this part into the front, but it's basically saying the same thing. It's called Leibniz's notation. So that is this is one way of writing down derivatives, and we will definitely use this a lot when we are talking about proofs of derivative properties. Typically, because this definition is this notation is very intuitive, and so using an intuitive notation in proofs helps a lot. So I will be using it then. I will also be using it when I'm talking about second derivatives a lot. So that's also something we will get to later in this course, and integrals. You will also see this dx come back in integrals when we are talking about that. Okay. Then there's the second notation that is probably the default, most commonly used notation. It's f, then this apostrophe of x. So this means f. Yes, Ria?
I couldn't hear you for a moment.
Wait, can you please say that again?
I couldn't hear you for a moment.
Okay. So I will repeat that again. This notation right here is the standard derivative notation. So this is how I will write down derivatives the most, and it's pronounced f prime of x. So it's written f this apostrophe symbol of x. Just like we can write f -1 of x to denote f inverse of x, this means f prime of x, and this just means the derivative of f of x with respect to x. So this is kind of the default notation. It's called Lagrange's notation, and this is we will use this also a lot in this course. So if you see this, it means the same thing as this notation for a derivative. Then there's this third notation that Newton used. It's rightfully called Newton's notation, and it's f the dot over the f of x. So this is typically used a lot in physics, in science, and so on. We won't use this one a lot, but if you see this, you would know that that is a derivative. So we will use it, but not as much as the first two. But if you take calculus later on, you will definitely need to know this notation. And if you want to study physics later on, you will also need to know this notation. So these are the three ways we can represent derivatives, and they all are equal to the limit definition that we talked about earlier. Okay. So when I was first studying derivatives, a natural question that I asked was, can a derivative not exist? So how would that happen? At what point would the derivative not exist? And what this means is we can't draw, or we can maybe draw a tangent line to the curve, but we might not know what its slope is or something like that. So the first case is if a function is not defined at some point. And if a function isn't defined at a point, then it doesn't make sense even talking about the function at that point, much less certain properties such as a derivative that it has at that point. So of course, the derivative doesn't exist if a function is undefined. The second case, if a function is not continuous, then we cannot differentiate it. So here I drew this absolute value graph with a hole here, and this type of discontinuity, by the way, can anyone tell me what this is? This type of discontinuity right here?
Hole?
It would be a hole if it wasn't defined, but so there is a, like, I guess you can call it a hole, but a hole would be if the function wouldn't be defined there at all. But here you can see that the function is defined. So this is called a point discontinuity, because there's a hole, but the function is defined at some other value. A true hole would be if a function isn't defined at all. But this is discontinuous, and it is a point discontinuity or removable discontinuity. And you can't really think about a derivative here because, or a slope of a tangent line, because to draw a tangent line to a graph, you need two infinitely close points. And you can't really draw a line through this point because there are no infinitely close points to this point that lie on the graph. So because of that, the tangent line doesn't exist, and the derivative also doesn't exist. So that's also really important. If a function is not continuous, then the derivative does not exist. The next case, if there's a sharp point. So notice this absolute value graph's V shape, right? That's very characteristic of an absolute value graph. And well, if you see a V shape in math, it means that it's an absolute value curve. But notice that here we have a sharp point. It doesn't like gently move into this branch of the curve. It sharply turns at a 90-degree angle. And when that happens, there's also no derivative. Because think about drawing a tangent line to the curve through this point. So suppose that we have this one in blue. Yes? Yes, that's a good point. If you graph the derivative, it goes directly from -1 to 1. So right now I will definitely get into the technicalities of all that in the next class, which it will be basic derivative rules. We will talk about derivatives of constant functions and linear functions. But for now, I want to kind of get a more intuitive understanding of why this derivative doesn't exist. But that's a really good point. It's because it jumps from -1 to 1. So if you think about drawing this blue line right here, then you can note that right, there are infinitely many lines that go through this point, and all infinitely many of them have infinitely close points along the graph. For instance, you could debate about what the tangent line will be here. It could be a continuation of this line, it could be a continuation of this line, it could be this line right here. In short, it could be any of these infinitely many lines. And because of that, the slope is undefined. We don't really know what it is. And this isn't the only case. Whenever we have a sharp point in math, so kind of a point where the function suddenly changes, it doesn't slowly, gradually change it to the next branch. It changes at an angle. In that case, the derivative is also undefined. Notice from all of these things that continuity doesn't imply differentiability, because this function was perfectly continuous at this point. There was no jump, hole, point, asymptote, there was nothing like that, but it was still not differentiable. So continuity doesn't imply differentiability. If a function is continuous at a certain point, that does not mean that a derivative exists at that point. On the other hand, if a derivative exists at a point, then we know automatically that the function is continuous. So this is a very important fact. We will definitely use it later on in this course in other proofs. So differentiability implies continuity. So I want to talk about this idea a little more. So our statement is, if a function has a derivative that is defined at a point, then it is continuous at that point. So there is a kind of mathy definition, but it involves another definition of a derivative, and I don't want to go into that just yet. in the homework problems, there will definitely be some problems related to that. But really, right now, I want to kind of get an intuitive explanation of why this works. So I want to give you 5 minutes and see if you can like think about a reason using what we know for why a function being differentiable would imply that it is continuous at a point. So I'll give you 5 minutes to do that and to think about that question. Why is that true? And then you can write your answers to me in the chat. And yeah, so I will pause my share screening. For some reason, it's not. Let me pause sharing. Okay. Yeah. So I'll give you about 5 minutes to think about why this is true. And then you can type your answers to me in the chat. Okay. So I'll give you about maybe another 30 seconds to write your answer in the chat. Okay, can you write the question in the chat? I will write it in the chat in the meeting. Why does the question is, why does a function being differentiable the point imply that it is continuous at that point? Okay. Okay, so I'll go over how I would approach this problem and how we can actually rely on more than intuition to solve this. So here we will talk about a common proof technique. It's called proof using a contrapositive. So if we have a statement, like suppose that the statement is if A then B, the contrapositive of that is if not B then not A. For instance, if A then B, right, could be if it's cloudy then it's raining. The contrapositive of that is if it's not raining then it's not cloudy. So that is what a contrapositive is. And the thing about a contrapositive is that if a contrapositive of a statement is true, then the actual statement itself is also true. And the reason for that is because the contrapositive of the contrapositive is the initial statement. If we negate this and put it there, we get B. If we negate this and put it here, we get A. And so if we have a statement that we want to prove, we can find the contrapositive of that, see if that's true, and if that's true, then the initial statement is also true. For the statement that we want to prove, if a function is differentiable, then it is continuous. The contrapositive of that is if a function is not continuous, then it is not differentiable. So this is true. We looked at several cases where if you have an asymptote or a hole, then the function isn't even defined there. It can't be differentiable. If there's some other discontinuity, like a point discontinuity, we look at that too. There are no infinitely close points to that single point discontinuity, so no tangent line exists, and so on. So if there's a jump, of course, there is also a finite gap. There are no, the limit doesn't even exist, so it's obviously not differentiable. So if a function is not continuous, then we know it's definitely not differentiable. Because of that, we know that our initial statement, if a function is differentiable, then it is continuous. We know that that is also true, because this statement is the contrapositive of this true statement. So this is, once again, this is, you might say that there's not really a lot of math involved in this, and you're right, there isn't. The reason for that is because the more mathy definition, the more mathy proof for this involves a different definition of a derivative that I don't want to get into just yet, because we're still trying to get our feet wet with this idea. So, in the homework, I will try to introduce some of these topics, and it is important that you do this homework, especially because, or at least look at it, maybe not do the problems, but definitely look at it, because some of the concepts on the homework will be new. They won't be taught in class, but they will be introduced using concepts that will be taught in class. So definitely look and do the homework problems. But the non-mathy definition without that other definition of a derivative looks like this. So this is how we would prove that differentiability implies continuity, and we will use this fact a lot, like a lot. We will use this fact, and it will basically be present in a lot of proofs that we will do later on in this course. Okay. So this is about it. So oh wait, my share screening was paused. Okay. Okay, so this is, I forgot that my share screening was paused, so you couldn't see the slides, I guess. So this is how you would write this. This is essentially how we would prove this using the contrapositive. So if a function is not continuous, then it is not differentiable. That implies that if a function is differentiable, then it is not continuous. And since the first fact is true, the second fact must also be true. Okay. So recap, because we are about done. So a derivative of an output with respect to an input is the instantaneous rate of change of an input with respect to an output with respect to an input. For instance, a derivative of distance with respect to time is the instantaneous rate of change of distance with respect to time, which is instantaneous velocity. And we calculate that by finding the slope of the tangent line to that function. So a derivative of a function at a certain input is the slope of a tangent line to that function at that input. And we think about all of this by thinking about drawing a line between a point and another point that is infinitely close to it. And one of those points could be x comma f of x. The other one could be x plus h comma f of x plus h. And because of that, we can use the rise over run definition and find the limit as those points get infinitely close to each other. And then we can actually define a tangent line and we can talk about derivatives. So these are the different notations for a derivative. They all mean the same thing. They all mean this definition right here, the slope between 2 points that are infinitely close. So this right here is 2 examples of the Leibniz notation, and this is Newton's notation. This is Lagrange's notation, f prime of x, and we will use all of them in this course, some to varying degrees, but we will use all of them. So you should definitely know all of them before we move on further. And then the other, yes. Oh, I'm actually not done just yet. But yeah, we're not done just yet. So I don't know. So the other fact is, yes, yeah, we're not done just yet. So the other fact is that differentiability implies continuity. Once again, a function being continuous does not imply that it's differentiable. We saw it with sharp points. If there's a sharp point, then the function is not then the function is not differentiable, even though it might be continuous. But if we know that a derivative is that a derivative exists somewhere, then we know that the function is continuous. So this is just about it. This is the end of the presentation. So I'm going to stop sharing my screen.
Thank you. Bye.
Does anyone have Does anyone have any questions before we go about the homework, about anything, about what we will do later on? No questions? Are you sure? Okay, when will we go over the continuity homework? Okay, so the continuity homework is due next Friday. So all the homework is due a week later. So we will go over the continuity homework at the beginning of class next Friday. But if you have any questions before then, you can always email me and I will try to answer them as fast as I can. Yeah. Also, I noticed that a lot of you have not yet done the limits homework. Definitely do it. If you have, because I mean it'll definitely help you. You won't really gain a lot just by listening to my lectures, right? So you really need to practice calculus if you want to learn it. So I know that a lot of you may be familiar with limits, but I know a lot of you aren't. So for those of you who aren't, definitely check out the homework. If you need to rewatch this again, the recording will be posted on Classroom. So that's just about it. Any more questions? No? Okay. So I will also post the homework for this lesson that will be due next Saturday. Today I will post that today. Okay. And the continuity homework again will be due next Friday, where we will, and next Friday's class will be about introductory derivatives, so like basic derivative rules and stuff like that. Okay, so that's about it. Thank you so much for coming, and if there are no further questions, I will end the meeting. Okay. Have a good day.
Bye.